Homework 11, Polynomial Functions, Video 3. We're going to be graphing some polynomial functions and what I like to term ungraphing them, but before we do either, we should look at some characteristics of graphs of polynomial functions. There's three things in particular I would like for you to know. Number one, the graph of a polynomial function is smooth and continuous. Now, there are rigid mathematical definitions for both of these words, but we're going to think about them intuitively. What smooth means is that there are no corners. For example, the graph of absolute value of x is not smooth because it has a corner. Continuous means that it's not broken. And believe it or not, there are functions whose graphs are broken into two or more pieces. Think about when we found the domain of a rational function, where we had a fraction and we had to find the value that made the denominator 0 and throw it out. Graphs like that will have broken graphs or discontinuous graphs. But polynomial functions are smooth and continuous, meaning that no corners, and don't pick up your writing utensil and resume drawing the graph elsewhere. So this is an example of smooth and continuous. And here's an example of not smooth. Sharp corner. And here's an example of not continuous. In order to illustrate not continuous, I'm going to draw a dotted line, have a graph approach it and shoot upwards, and then on the other side, resume from the bottom. That graph is broken if you consider that collection of branches a single graph. So, smooth and continuous, no corners, no breaks. Characteristic number 2 of the graphs of polynomial functions. Each end either rises, which means it points up, or falls, which means it points down. The directions that the ends point is called the end behavior, and one of the things we're going to be doing in a moment is predicting in advance the end behavior of the graph of a polynomial function, meaning does the left end rise or fall, does the right end rise or fall. So for example, if we had a polynomial function that resembled a parabola, we would say that the left rises because it's pointing up, and we would say that the right rises because the right end is pointing up. Personally, I take a little issue with this description because when you read a graph, you typically read it from left to right. So as you're coming in, you're actually moving downward, even though we say that the left rises because it's pointing up. Or if we had something like this graph, then we could say that the left rises, but the right falls. This is equivalent to when we discussed the graphs of quadratic functions, parabolas, about predicting in advance whether the parabola opened up or opened down, which would, in this context, be both ends rise or both ends fall. But with polynomial functions, the ends can do their own thing. They don't necessarily have to agree with each other. Sometimes they will, and they'll both point the same direction. Sometimes they'll disagree with each other, and they'll point opposite directions like this or like that. And the third characteristic of polynomial functions is called turning points. If the degree is n, then the graph can turn up to n minus 1 times. So whatever the highest power is, if you subtract 1, that's the most number of times that the graph can change directions. For example, let's say that your degree is 3. this means that the graph can turn up to 2 times. There's no guarantee it would turn 2 times, but it can't turn more than that. An example of a graph that turns twice, let's start with the left end falling. So the graph goes up, turns, goes down, turns, and then goes up again. Or it could do something like this. I'm going to start by the left end falling, go up, have a slight bend, and then keep going up. So this graph would turn 2 times, this graph would turn no times. At no point did it change its vertical direction. Or if you had something like degree equals 4, that could turn up to 3 times. So we could, let's say we have a graph that rises on the left. So the graph starts moving downward, we're going to turn 3 times. 1, 2, 3. That's an example of turning 3 times. Or maybe it would just turn once, like that. Now if you're wondering if the degree was 4, could it turn 2 times and look something like this? The answer is actually no, and the reason is when you lose a turning point, you actually lose them in pairs. So imagine that you wanted to lose this turning point here by flattening out the middle, then you would have to lose the turning point that follows it. So if I flattened it and lost one turning point, I would actually lose 2 of them. So when I say up to so many times, that means anything less than that, but you actually lose turning points in pairs. For example, this has 2 turning points. If I flatten it out, it has no turning points. Plus, our discussion about end behavior would prohibit something of degree 4 from actually turning twice and looking like that, which we'll discuss in the next video.